Bismillahirrahmanirrahim. In the last class, in the last part of the class, we have discussed on the upsampler, where we have discussed on the plot in the frequency domain. If we do the upsampling of a arbitrary signal xn, so how it looks like, we already know how it looks like in the time domain, and from the time domain presentation, we already can expect that the frequency will be decreased with a factor of L, where L is the factor for the upsampling. So in the last class, in the last part, we have sketched this frequency domain behavior, and we have mentioned that after doing the upsampling, we need to be careful about the other frequency component that can be merged inside the pi. That means your range of view. So according to that, we need to design our filter. So that was the last part of our last lecture. Okay, if you have any question or comments on that topic, you are welcome to ask. Okay, so if you don't have any question at this moment, we can move forward. This is our next topic, that is inverse Fourier transform. Okay, in a different way we can perform that, and as I have already mentioned that these lectures, that means the lectures for the Fourier transform and the inverse Fourier transform, is not to just do the mathematical part. We need to understand the concept. So we are focusing on the concept mostly. Here I have given a simple example how we can do the inverse Fourier transform, and mostly we'll try to cover that, how to solve those for a particular engineering problem. For example, if we have this as the frequency, after having the Fourier transform, x omega is given as j sine omega multiplied with 3 plus 4 cos omega plus 2 cos square omega. So by the notation, you can find that this is in the frequency domain. Here, of course, we need to find the xn. We need to find the xn. So, of course, if we have xn, we do the Fourier transform and we find x omega. If we do the inverse Fourier transform from the x omega, then we'll get back to our original signal in the time domain. So that is our target. So we can elaborate this by understanding this concept. We can find the result. That means our target is to find xn. We can find the value for the xn. Let's start. First of all, we can elaborate this function by using Euler's formula or Euler's identity. As you can see that the sine omega can be written as e to the power j omega minus e to the power minus j omega divided by twice j. There is with twice j, and since there is another j before that, that will cancel each other. So that's why we can write it like this. So this this whole part can be written as this. Then we have 3 plus 4 cos omega can be written as e to the power j omega plus e to the power minus j omega divided by 2 plus again the cos square omega. So we twice cos square omega. So cos, this is a cos part, so we can write it very easily. Okay. Now we can expand more by the trick, by the formula. We can expand more, and after expanding, we can find the values like this. Okay, if I write it here, so it will be like 1 by 4 e to the power j3 omega plus e to the power j2 omega plus 4 by 7 e to the power j omega plus there would be no value of e to the power 0. That means that is 0. 0 is the value. Then I'll explain this, and then after the 9/2 e to the power minus j omega plus, or you can say minus e to the power minus j twice omega minus 1/4 e to the power minus j 3 omega. Okay, from each and every notation, we can understand. Okay, for example, this is 9/2. Then 9/2 multiplied with e to the power minus j 1 into omega. This is actually 9/2 e to the power minus j n omega. So what is the value of n here? The value of n is equals to 1. So that is the first sample. That shows that the first sample location, and this is the value for n is equals to 1. Similarly, for this one, e to the power minus j 2 omega. So then this is the value of n. So we can find that the value of the value at the location of n equals to 2 is equals to minus 1. So because there is a minus, and what is the coefficient? The coefficient is equals to 1. So we have minus 1. Similarly to this, what is the value of n? The value of n is equals to minus 3, because we have minus j3. Sorry, the value of n is equals to 3. So this is for n equals to 3. And what is the value? And the value is minus 1/4. So we are putting like that. Similar to this, if we don't have any number, so if we don't have any value like e to the power minus j n, what is the value of n at the 0 location? That is 0 into omega. So it actually gives e to the power minus 0. It will give 1. But if there is no number like this, that means there is no coefficient. So there is no coefficient. If you elaborate this function, the function what I have written here, if you elaborate this, you will find no value like that. So that's why we have 0 at the n equals to 0 location. Similarly, for 4/7, what is the power of n? E to the power minus j omega n. What is the value of n for this? That, of course, the n is equals to minus 1. N equals to minus 1. So that's why this is at the location of minus 1. Similar to that, if we have put e to the power j twice omega, it is equivalent to e to the power minus j minus 2 into omega, isn't it? So it is equals to e to the power j twice omega. What is the value of n in this case? The value of n is equals to minus 2. And what is the coefficient for that? The coefficient is equals to 1. So for n is equals to minus 2, the coefficient is equals to 1. So in this way, we can elaborate this, and by knowing this the power, we can understand that, okay, what is the value for that particular location of for different value of n. So this is the way how we can find the inverse Fourier transform. This is one way. There are different other way people can do the Fourier transform, the inverse Fourier transform. Okay. So the properties of the Fourier transform, I would like to request you to jump to the book. So read it from book. So we are following the book from the Crockies. This is chapter number 4. You will find the properties of the Fourier transform over there. So I'm just discussing few of those here in this lecture. However, you can find more in the book chapter as well. Okay, so we are just mentioning that you can go through the properties from the book, and the properties are most important properties are the linearity, number one. So which mentioned that if you have the time domain sequence Gn and Hn, and they are multiplying with a constant coefficient alpha and beta, if you do the Fourier transform, so it will convert it to G omega, H omega multiplied with the same coefficient. So this is according to the linear property. This is true for the LTI system. Time shifting, if you do the time shifting in the time domain, of course, that will make what kind of changes? They will change in the frequency domain. They changes the phase. So the phase represented by e to the power minus j n0 omega. So how much that will shift? As I have already mentioned that if you have a delta function in the time domain, let's say delta n, this is n equals to 0. What is the value delta omega? What is delta omega? Delta omega is equals to 1. That means you have all the frequency component in the frequency domain. It looks like this. What about the phase? You have the phase component. That means there is 0 into j. So you can find the phase component, and the phase component was 0 for all the value, if you can recall the previous sections. So here is the phase plot, and this is the magnitude plot I'm talking about. And this axis is omega, and this axis is omega as well. Okay. However, if we shift our time domain sequence one sample like n minus 1, in that case, what will happen? Whether this magnitude response changes, the answer is no. The magnitude response will remain the same, but there will be one term will be added, and that is e to the power j omega 1. 1 is for this one. If I give you the example here, delta n minus 1 e to the power minus j omega n. So by definition, this is from n is equals to minus infinity to plus infinity. That is the definition of that one. So for which value of n it is true? For n is equals to 1, this is true. So in that case, the amplitude is 1, and this will give you, this is e to the power minus j omega 1. N is equals to 1. So the value of del omega, so whatever the things, so if this is xn is equals to del n minus 1, in that case x omega is equals to this. Previously, if xn is equals to del n, we found x omega is equals to what? 1. However, for x is equals to del n minus 1, we have found that the amplitude will remain the same, 1, but there will be a term multiplied with that e to the power minus j omega 1. So from there we can write it very easily. If we have xn is equals to del n minus n0, what will happen? X omega, it will be 1 is the amplitude, and then e to the power minus j omega n0. So that will be multiplied, and since n this is for n is equals to n0, you'll got this term. So by doing that, by knowing this fact, we can understand that if that is shifted for n0 samples, so we got this multiplied with the value of g omega, where g omega actually came from gn. The Fourier transform of gn, Fourier transform of gn is capital G omega. Okay. Frequency shifting, you can also show that definitely if we have frequency shifting in the frequency domain, try to understand if we are in the frequency domain. So we are talking about, let's say, G omega. If we have the frequency like this at the location of some value, okay, let's start with this. We have the value at 0, let's say DC value. If we shift it for omega 0, that means what we are doing, you are introducing some frequency component. You are introducing some frequency component. So that means it is sort of frequency. Definitely, this is a frequency shifting. How it actually been observed in the time domain, that will be observed with a multiplications of the frequency component, with the multiplications of the frequency component. So it has been very simple to observe that if we are shifting the frequency in the frequency domain, that is equivalent to the multiplication in the time domain sequence with e to the power j omega 0. That means the frequency you have shifted. So the proof is given in the book as well. So if you found difficult, then of course we can discuss about this. Differentiation. Okay, I'll talk about this differentiation with the example. However, we can mention it. The differentiation of the Fourier transform value in the frequency domain with respect to omega, of course, multiplied with j is equivalent to n into gn, where of course gn in the time domain and g omega is in the frequency domain. So we can prove it within a few seconds. And the convolution, as you know, that the convolution in the time domain is equivalent to multiplications in the frequency domain, and which make our life very easy. Here, just I have proven the concept of the differentiation. Let's start with the basic equation. G omega can be written as this by the definition of the Fourier transform. What we have done Fourier transform. Now, if we do the differentiation in the both part, definitely we can write it like this. There is nothing to explain here. In this case, of course, this j part, this minus j part is not a function of n. That's why you can take out of this first bracket. So if I take a minus j over there, and minus j can be taken here as a minus j, and this minus j, if it is taken in the numerator, it can be replaced as j. So that is the part we have done here. And n is there, so this n is here, and we have gn, and we have e to the power minus j omega n by definition. So now from this equation we can easily wrote that this is our part which has been Fourier transform, and if you do the Fourier transform, it will be looks like this. So we can write, of course, we can write if we have ngn, do the Fourier transform, it will be converted like this. So we can mention very easily, if I want to do the g omega, that means differentiation value of in the frequency domain, it can be written like this as well, if we are not considering the j here, because from which part we got the j, we understand that. So in that case, we can write this j part should be here. Otherwise, we do the inverse Fourier transform. Whenever we are doing inverse Fourier transform, it will going to give this value n into gn. So that is the relation between due to the Fourier transform in the frequency domain to the time domain. By using that concept, now we'd like to do one Fourier transform of a practical example where it is given that the xn is equals to n alpha to the power n un plus 2, where alpha is less than 1. First of all, try to understand the signal itself, how it looks like. This is, of course, a unit step function, but it start from the location n is equals to -2. If I have something alpha to the power n un, it start with the location n is equals to 0. Based on the value of alpha, whether it will decrease or it will increase, but it will start with at the value of n0. But since it is multiplied with n plus 2, where it will start. So at the location of n is equals to -2, we have the value. For n is equals to -2, the location is u0. For n is equals to -1, okay, n is equals to -1, we have u -1 plus 2, which give u1. What is the value of that? Of course, that is equals to 1. So I believe that you understand un plus 2, that means it is shifted 2 sample to the left. As we have already know that alpha to the power n un, if you do the Fourier transform, you got this result. We have already performed this, so we are not doing this anymore. Now what we can do, we can elaborate this xn function for different samples. Let's say this is for n is equals to -2. At n is equals to -2, what will be the value? -2 n alpha to the power -2, and then u -2 plus 2, which means that -2 alpha to the power -2 u0, that is equals to 1. So at the location of n equals to -2, we found -2 alpha to the power -2. Similarly, for n is equals to -1, what we can find? -1 alpha to the power -1 u -1 plus 2, which leads to alpha to the power -1, and that's it. And there is a, of course, minus, because we have a minus at the starting point. So we have minus alpha to the power -1. At the location of, from the location of n equals to 0 to infinity, we have this, because at that moment, if you put n equals to 0, n equals to 1, 2, 3, whatever the value, so 0, 1, 2, 3, any value, for all those things, this is equals to what? This is equals to 1, and that will be valid for the result. Okay. So there are 3 sections we found for n equals to -2, -1, and then in general, we got this expression. Now, what we can do the Fourier transform of this. We can do the Fourier transform of this, and we can do the Fourier transform of this, and then we add those together. Because why we can add those together? Because according to the linear operation of the Fourier transform, you can do the Fourier transform of each and every particle and then add together. Okay, if you have x1n plus x2n, so what you can do, you have x1 omega and then x2 omega. That's good. If you have multiplied with some constant alpha, it will be also there. If you have a beta there, it will be there. So according to that, we can do that. So first of all, we need to do the Fourier transform of this part. So what, by definition, what is the value? We have, this is xn, and then multiplied with multiplied with e to the power minus j omega. What is the value of n? Minus 2. Try to remember that in the basic definition of Fourier transform, we are putting in general n is from minus infinity to plus infinity, then xn and e to the power minus j omega n. Whenever the n is a particular value, that means there is no range. What is the range of n? N is only minus 2. Then what will be the value? The value will be here at the location. What is the value? That is your xn, that is minus 2 alpha to the power minus 2. That is your xn for a particular location minus 2. And then e to the power minus j omega. What is the value of n? That is minus 2. So we can write it like this. Plus, again, this one is your xn. So this one multiplied with e to the power minus j omega minus 1. And then the third section, if you can remember that this is this form is known to us. Okay, n into gn is equivalent to this one if you do the Fourier transform. So this is known to us. So now we can use this formula. So n alpha to the power n un. We know this Fourier transform of this part. We have already known that, and this is the format. So if we consider that, okay, this is our what? This is our gn and n into gn. What would be that? The Fourier transform of gn. Fourier transform of gn. What is the Fourier transform of gn? The differentiation of gn is, this is g omega. This is g omega. And if we have n into gn, that will cover d omega, and there will be multiplication of the j. So as I have discussed here, we know this Fourier transform is this one, and then that will be differentiated with respect to omega and multiplied with the j, because we have that format. So if you consider this one as n into gn, we can do the Fourier transform, and that should be looks like this. We have already proven that. So from there, okay, what you need to do, you need to perform this differentiation. So perform the differentiations, and then we have found this result. And after finding this result, you can elaborate this. And as we have already mentioned that based on the power of E, you can find that what is the location of that value. What is the location of that value? So we have find this result, and this is actually your x omega. You can plot it with respect to different value of the omega. So you can plot this x omega for different value of the omega, starting from 0 to pi, that is enough, or 0 to minus pi, because that is our range of view. And this is how the differentiation can help us for a particular problem when there is a multiplications are given with the value of n. There are a lot of examples in the books or in the online, so you can find it. Though I'm not encouraging to do a lot of examples from only just to do the Fourier transform and inverse Fourier transform, because it actually not help us in any way for the DSP class. However, for the mathematics class, math class, it actually helps. So what is our focus again and again? Just to understand the real concept from the time domain to the frequency domain. You can use your practical experience, and you can use the MATLAB just to plot different values in a way, and you can justify the result. I would like to request you to justify all the characteristics with some example and plot it in the MATLAB, and that will help you to understand what I am telling. That please please give the input, produce the input in the time domain, and try to see how it looks like in the frequency domain. By the frequency domain behavior, try to understand those properties. That will definitely help you. Okay, so that will help you in the long run, just to not to memorize the things, you can understand the things as well. Okay, so that is the end of the Fourier transform part I have completed. So I want to concise our lecture up to this. After this, I will start the Z transform. So today I will just start the introductory part, and then try to concentrate on the other part as well. So before move on to the Z transform, do you have any question or comments at this moment? Okay, let me start the Z transform. The topic name is Z transform. Probably you can find it in the chapter number 3 in the Procrea's book. Okay, so always it is mandatory to go through the book as well. Other sources, the available sources are there. First of all, what is the motivation to start or read the Z transform? Number one could be like this. It is a very powerful. This is a very powerful transformation by which you can design the filter very effectively, and I would say very confidently. So this is a tools by which you can design the filters. Designing filters by the Z transform is very convenient and effective. Number one. And number two, which is the main purpose of the Z transform, is that to understand the stability of the system. Try to understand stability of the system, not stability of the input signal. Whenever you are giving some input to your system represented by H omega or Hn, that means the impulse response, and input is X omega or Xn. Due to that, you are find Y omega or Yn in the time domain. Whether the system is stable or unstable, of course, it depends on the impulse response as well as to the input. Because the stability means your output is stable, unstable means your output is unstable. For a particular input, your system might be stable, or for another input, the system could goes unstable. So the stability of the system actually refers to both the input and the impulse response. Of course, you need to find what is the impulse response, and as well as you need to tag for which condition this system will remain stable. For example, I have probably I have given this example to you when I have talked about the stability. Like if you have a car, you are driving a car. So you are driving this car with a particular speed. And let's say the speed is 150 kilometers per hour. And you are running your car very smoothly and fine. So the system is stable. What is your input? The input is acceleration. And which one is your system? The car is your system. So now when you are giving more speed or acceleration more and more, and you reach to very close to 300 kilometer per hour, then you found that the system is very close to unstable situation. So for a small change like 301 kilometer per hour, your system is fully unstable. So you are having the same system there. However, due to the different input, once the system was stable, and in another situation that will be unstable. So the stability of the system depends on both the system itself as well as what kind of input you are putting for the or in what kind of input you are given to the system. Okay, so here the Z transform actually gives us the essence of the stability of a discrete system. This is important. To find out the stability of the analog system like XT, what is the tool? Could you please mention the name of the tool by which you can find the stability of an analog system, a continuous time system? Any of you? What kind of tools or tool you have used to understand the stability of the analog system? Yes, 130.
So Laplace transform.
Excellent. This is called Laplace transform. What actually you understand from the Laplace transform? So how many planes you need for representing the Laplace transform?
So there are two axes. One is omega and one is sigma.
One is real, one is imaginary. Yes, then
the imaginary is omega oscillation and real is sigma decay.
Sigma, yes. Do you need the z-axis?
No, sir.
Okay. Of course, you need the z-axis as well, because you are mentioning, let's say, these are the pole location. So the pole location, how you are actually representing the pole location, that shows that it is an infinite value. So you have highest value over there. You have highest value at this point. And where is the lowest value? How you can represent that? So in that case, okay, let me draw a small piece of value like this. So if I'm at the floor, this is the imaginary axis and this is the real axis. As your friend already told that, okay, this is sigma and this is omega. I'll just draw this part and then I'll explain the thing. Let's say this is my poles. Poles means at that location, this value is very high. Let's say the values are very high. Before that, what will be the value? It's a bit lower, but forming the same value or close to that. So you are presenting something and maybe it's very flat. And after this hill, how the other value looks like? Let's say the other values in the background, they looks like this. Okay. So they are again smoothing like that. So whenever the alpha is changes for a particular value of alpha and omega, you are getting a very high peak. You are getting the high peak value, so like this, and which is very close to infinite. So that means you need actually a z-plane representation as well for the Laplace transform, which we have mentioned it like this. We have the real and we have the imaginary, and we are plotting it like, okay, this is poles, those are the imaginary poles, and let's say this is a 0. So we have made it like two-dimensional, but actually it must be three-dimensional things. So I would definitely prefer you to understand the Laplace transform with graphical representation, as I believe that at this moment you have proper idea on continuous time Fourier transform, how graphically you understand those things. Please understand the Laplace transform also graphically. If I give you very simple example of the Laplace transform or use of it, why we need that practically. Let's say you have a circuit, the inductor, capacitor, and the resistor. For a particular value of LCR, RLC circuit, for a particular, let's say this is a DC input. For particular values, you definitely have three kind of solutions or three kind of signals. Number one, it might have this. The signals might looks like a sinusoidal but decaying with the time. So you have some damping factor. Due to the damping factor, it will decay. So this is case number one. Case number two, it can be like this. It will increase over time. So let me start with this. Okay, whatever the case, it will increase over time. Okay, so it might happen. Number two. And number three is that it can be stable, not stable. This is called the critically stable situation. So you only have the sinusoidal signals like that, where the magnitudes are remain the same. So if you consider the first case, that means it actually gives the stability of the system. And the second case, this is unstable situation for the circuit, because in some moment it will burn because the voltage is increasing more and more. That will dragging the current as well. So if I plot this as a current, so the current is increasing in the second case, so it will burn anyway. And okay, this is critically stable. It can goes in any way. It can goes like this, or it can be goes like that, based on the damping factor by changing the value of R, or a combination of RLC. Okay, so now according to the Fourier transform, we can only understand what is the frequency of, what kind of frequency it generates, this circuit generates. That means in red line, case number one, the red line, what is the frequency of this sinusoidal signal? You can find it by what? If this signal is xt, if the signal is xt, then xt multiplied with e to the power minus j omega t. And I believe you know that what is e to the power minus j omega t. This has two parts, real part cos omega t, imaginary part sin omega t. Then you are multiplying those two, and you are finding the area under the curve by multiplying, and then you are summing up all those things. That means you are doing minus infinity plus infinity and dt. So you are doing the Fourier transform. This is exactly the Fourier transform of xt. You are doing the Fourier transform, and by which you can understand what? You can understand, let me draw the diagram here. Okay, you can understand if this is omega, because this is analog part, let's say omega, you can find, okay, you can find a peak. And what is the value? Let's say this is the peak you have found. So that means you have a frequency, and of course in the negative direction you have another one, just for the mathematical concept. Now there is a problem still in the Fourier transform. You can't understand whether this signal is stable or unstable, or if that is stable, for which factor it will shows the stability for that one. So in that case, we have add another factor with xt, that is xt multiplied with e to the power minus j alpha, not j, there is a real part, so alpha t. What we have done previously, your signal maybe looks like xt, it was a sinusoidal signal. Okay, so this is a sinusoidal signal. Try to understand this part. What is xt? Now forget about this and forget about this. Let me erase this part. Let's say you have a pause signal like this, sinusoidal signal like this, which is a purely oscillating signal without any damping, and that is our xt. So this is our xt. Now what we are doing, we are multiplying this e to the power minus alpha t. If the alpha is positive, if the alpha is positive in nature, so that means 0.1, 0.2, 0.3, or even 1. So in all the cases, it actually gives some decaying signal. So it will give some decaying value like this. So when these two will multiply e to the power minus alpha t, those will multiply this alpha. We are putting alpha is equals to, let's say, minus 0.1, minus 0.2, minus 0.3. That minus will multiplied with the minus, so it will eventually gives plus. So that means I'm writing xt e to the power minus minus, so that is 0.1 into t. So of course this will be a decaying signal. Let's say this is that value e to the power 0.1 t, that will be a decaying signal. If you increase the value of alpha, that will decrease more and more. Okay, at this moment what happens, so now the signal, how the signal looks like, the signal should be looks like this. The xt now looks like this. Something like that. So now xt and alpha t, when we are multiplying this, the signal looks like this. Now the question is whether this signal is your unknown signal. Your unknown signal means your xt, whether your unknown signal xt is very close to this signal or not. That is our objective. That means you have your unknown signal like this. This is not actually the value we are looking for. We are looking for two values. One is what is the frequency, that is this omega, as well as we are also looking for what is the decaying factor for which it will match perfectly. If I go to the real plane and the imaginary plane, where the imaginary plane actually in the Fourier domain, this is what? This is omega, and this is the magnitude of x omega. This is the magnitude. This domain, that means I'm how I can show that this domain, this axis is now converted to that axis. So this is now this imaginary axis, nothing else. So previously, if you have the peak like this, a frequency component, let's say the frequency, okay, higher frequency and higher frequency like this. Now it will be converted. Okay, what is the value? Let's say this is omega 1. and this is omega minus 1. So these 2 points are now here. This is omega 1 and this is minus omega 1. And what is the value? What is the amplitude? That is missing here. Okay, that is missing here. That's why I'm telling that there we need a z axis as well. So that will be the perpendicular to this imaginary line. What would be the value? So what is the amplitude? We'll talk about this later on. But what about the alpha in this case? What about the alpha here? In this case, the alpha, that means xt e to the power minus alpha t, and let me erase this, and e to the power minus j omega t. Here the alpha is equals to 0. If alpha is equals to 0, this is equals to 1, and it is exactly the Fourier transform. And in that case, we are only targeting what kind of signals? We are targeting only the oscillating signal, do not have any decaying factor. So we are targeting this kind of signal in this pole or in this plane. Okay, now if we want to target this kind of signal, okay, sorry. So decaying signal, let's say we need to move which direction? We need to move to the left, because in that case, the value of alpha is negative. Value of alpha is negative, that makes it positive. Actually, it will e to the power minus alpha t. If I took alpha is equals to minus 0.1, that actually makes plus 0.1 t. So it takes 0.1 t. What does it mean? These two will match, whether it will match each other or not. So you have what kind of signal? You have this sinusoidal signal. Try to understand this part. I'm asking, this part has any oscillation? Yes or no? E to the power minus j omega t. What is the amplitude of that? What is the amplitude of e to the power minus j omega t? How it looks like?
So 1.
That is 1. And now you are multiplying e to the power minus e to the power 0.1 t with that signal. So how it should be looks like? It should looks like this. So this signal is nothing but e to the power 0.1 t into e to the power minus j omega t. This omega shows the frequency, and this alpha shows how fast it will decrease the amplitude. Now, what about your xt? Is that known to you or unknown? That is unknown. Now you are doing the convolution between this signal and your xt. If your xt is like this, let's say your xt is like this. It decaying very fast. It decaying very fast. Will this xt match with your value alpha is equals to 0.1? Will it match? No, that will not match. So that's why the amplitude will not vary. The amplitude, that means when you are matching those two in the integration, that summation will not give very high value. High value means infinite value will not be generated. If you are proceeding more to the left, then what will happen? Let's say alpha is equals to 0.5 at the location of 0.5. At the 0.5, the e to the power 0.5 t into e to the power minus j omega t. This omega should be omega 1, because at the omega 1 you have the highest match. It might looks exactly same as this one, so that will match each other. In that case, what will be the sum? What will be the integration value? what will be the integration value? The integration value will give you the maximum result, and that is called the pole location. Where is that pole location? At alpha is equals to minus 0.5. Alpha is equals to, of course, minus 0.5. And as we have already found that the omega is equals to at omega 1, you are getting the maximum value. And similarly, at the negative locations, you are getting this. In the positive direction, if you got alpha is equals to, let's say, 0.5, then it will got e to the power minus 0.5 t, and which is actually looks like a signal which is giving higher value when they are progressing. So this is over there. If your signal, even it might happen that if your signal, that means your xt is looks like this, then where, in which domain it will match? Definitely it will match in the right side somewhere else. So if your pole is in the right side, definitely it's called unstable signal. Of course, this kind of xt is unstable, and this kind of signal is stable. So in summary, what we can tell you, in case of Fourier transform, we just represent only the frequency component, nothing else. The stability, we can't show the stability. But in case of here, the real part is alpha and the imaginary part is omega, the frequency. In this case, you can both, if I put like this, that means the poles, what does it means? That the frequency component is this, where is omega, the frequency component is minus omega. That actually match with your unknown signal. Let's say the unknown signal is looks like this. This is your unknown signal. This is what? This is your xt. Where the frequency, what is the frequency? The frequency is omega 1. And what is the damping factor? What is the damping factor? And you can find that, okay, this is my damping factor minus alpha 1. That is your damping factor. Is that clear to you? What does the Laplace transform means? Can you explain the Laplace transform if I ask you in the Viva or in the quiz? Any confusion? If you have any confusion, I can repeat the things again for you. Okay. If I have yes or no, you don't have any reply. So how can I understand? Because this is an online platform, so I can't even see your face. So you should reply whether you have a problem or you don't have any problem.
Sir, it is clear.
Understood, sir.
Okay, understood. Okay, so if you have some signal, let me ask you one thing. If your signal xt, I'm talking about xt, is like this, there is no oscillation like that. This is xt. Approximately, can you plot the pole location in the Laplace domain?
Sir, on the negative real axis.
On the
Negative part of the real axis.
on the negative part of the real axis. It does mean that in case of xt, if we are putting e to the power minus j omega t and e to the power minus alpha t, this part, there is no oscillation, that means there is no frequency, so the omega is equals to 0. So since omega is equals to 0, where is that portion? So this is the portion, omega equals to 0. Now, what is the decaying factor? Let's say the decaying factor is minus 0.3. So where is that point? So let's say this is a minus 0.3, and there it actually match, the xt will match at the location of alpha is equals to minus 0.3 and at the location of y is equals to 0, and this is that location and that is the pole location. Whenever you have the signal like this, the oscillation like this, of course, in that case, you have the imaginary pole locations, and it might be here, and of course there are two poles, and of course there is a frequency because there is oscillations, and also there is a decaying part. So that's why you need some alpha portion as well. Okay, so I believe that is enough for today. In the next class, I will try to start with the Z transform in particular, because before going to the Z transform, since you have the experience on the Laplace transform, by definition the Laplace transform is xt e to the power minus st, and you are doing the integration from minus infinity to plus infinity, and this is for dt, where s is equals to sigma plus omega j omega. Okay, so you know those definition, but my basic concern was to the understanding, how much you can understand from the graphical perspective as well. So if you feel interested, you can search the internet, and in the YouTube you can find a few very good video lectures on the Laplace transform. So it's very important to understand the Laplace transform physically, and what is the purpose, basic purpose of it. The basic purpose of is to find the search the stability of physical circuit, the response of the circuits, the physical mechanical parts and the other things. By using the Laplace transform, we can find the stability. Similar to that one, by using the Z transform, you can find the stability of a discrete system like Xn. Okay, so in the next class, inshallah, we'll start with the Z transform. So thank you very much for your participation.